In this lesson, we'll learn about the reactions of alkanes. Alkanes have a general formula of CnH2n plus 2. So the first few of them are CH4, which is called methane, C2H6, ethane, C3H8, which is propane, C4H10, which is butane, and so on. These are the first 10 alkanes. The first reaction of alkanes we'll learn is the reaction with oxygen. When alkane undergoes a reaction with oxygen, whenever an alkane reacts with oxygen, it undergoes a reaction called combustion. A lot of other organic compounds and hydrocarbons go through combustion reaction. Combustion reaction is basically the reaction with oxygen. So for example, if methane reacts with oxygen, we get carbon dioxide and water. We'll have to balance the moles. We have 1 carbon, so this is balanced. We have 4 hydrogen, so we'll place a 2 over here, and then we'll balance the oxygen. So we have 1 oxygen over here and 2 over here. 2 over here and 2 over here. So we'll need 4 oxygen, so 2O2. So for alkanes reacting with oxygen, it forms carbon dioxide and water. So this is how we can define the reaction of alkanes with oxygen. We call this a complete combustion. There's another form of combustion which happens when the oxygen is limited. When incomplete combustion happens, instead of carbon dioxide being formed, we get carbon monoxide or just carbon. We call this form of carbon soot. So if I want to find what happens for incomplete combustions, so for methane, incomplete combustion will give you a carbon monoxide or carbon soot, which is just carbon. The water will remain the same. Now we have to balance the oxygen. We will balance the water at first. The hydrogen is balanced, the carbon is balanced. Now we have to balance the oxygen. We have 1 oxygen here and 2 over here, so we have 3 oxygen. So this will be 3 by 2. And for the incomplete combustion that produces just carbon, we'll have water over here. If I balance the hydrogen, I have to put a 2 over here. We have 2 oxygen on the right, so this will be 1. Now there's a trend in whether the complete combustion happens or incomplete combustion happens as we go down the homologous series of alkanes. And it depends on the ratio of carbon to hydrogen. So if I want to find the carbon to hydrogen ratio as we go down the homologous series, so CH4, C2H6, C3H8, C4H10 and so on. If I want to find the carbon to hydrogen ratio, for the first one it would be 1 by 4 or 0.25. For the next one it will be 2 by 6, which is 0.33. For the next one we have 3 by 8. This will be 0.37. For the next one it will be 4 by 10 or 0.4. So as we go down the group, the carbon to hydrogen ratio increases. And when that happens, the probability of combustion decreases. The chances of combustion happening decreases down the group. So if I had a heavy alkane, it would be less likely to undergo combustion. So as we go down the homologous series, the carbon to hydrogen ratio increases, and the chances of the alkane undergoing combustion decreases. The issue with that is, for incomplete combustion, the energy released is much less than when complete combustion happens. The carbon monoxide is also a small problem, but if we are releasing it into the air, the concentrations will be very low for it to become harmful. Now we are seeing that as we go down the series or the homologous series, the chances of complete combustion decreases. However, we do not use methane as the car's fuel, we use octane. Why is that? The issue is methane over here is gaseous. So this is a gas. At room temperature, methane is a gas. The problem with gases are that it takes a lot of space and it's harder to store, and it's quite dangerous if it's in compressed form, and it's harder to transport them. If I wanted to transport some liquid fuel, I could just take it in a bottle and carry it around. I cannot do the same with a gaseous fuel. So that's the issue. I'd need pipes built for transporting them, which is a much larger hassle than liquid fuel. Octane is a liquid at room temperature, so it's much better at and much easier to store and much more portable than gaseous ones. So even though it has a larger carbon to hydrogen ratio, where the chances of complete combustion is less, the benefit of it being portable and easily storable outweighs the fact that it's not as good at combustion. So this is what we were discussing. We were discussing the fact that as we go down the alkane homologous series, the chances of complete combustion keeps decreasing, yet instead of the first one, so methane, which has the highest chance of undergoing complete combustion, we use octane, which is much farther down the group. So octane is C8H18. So instead of using CH4, we are using C8H18 because it's a liquid. Octane is a liquid, whereas methane is a gas. This is the reason we use octane and not anything further down or further up. That's why octane is a very good alkane to use as a fuel. Now the next reaction we'll learn about alkanes is their reaction with chlorine in presence of UV light. So if we look at the reaction of methane with chlorine, and we must need the presence of UV light here, we'll learn about that later. We get a mixture of different products. So after the first reaction, we get CH3Cl. So one of the chlorine replaces one of the hydrogen, and this hydrogen reacts with another of this chlorine to form HCl. This compound can again react with chlorine. Now it will form CH2Cl2 and another HCl. It will keep repeating until we have replaced all the hydrogen with chlorine. We'll have all of this in our product mixture. So now we have CHCl3, and finally in the last reaction we'll have CHCl3 reacting with chlorine to form CCl4 and HCl. The name of this over here is chloromethane. The name of the second one is dichloromethane. The di means there are two of them. We have two chlorine over here, so dichloro. The third one is trichloromethane. The last one can be called tetrachloromethane in the same form. Tetra stands for 4. Since this one has no hydrogen, we can also call this carbon tetrachloride. So carbon with 4 chlorides. Now why do we need the ultraviolet over here? The ultraviolet light basically causes a free radical substitution of the UV light causes the chlorine molecule to undergo homolytic fission. The homolytic fission basically means that over here there was an electron pair, so maybe this one came from the red chlorine, the dot came from the blue chlorine. When UV light strikes here, so we have UV light coming over here, this causes one of the electrons to go back to this chlorine and one of this electron to go back to this chlorine. Now when we write a mechanism, a full arrow means 2 electrons. A full arrow means the movement of 2 electrons, and a half arrow means the movement of 1 electron. So if I have a chlorine-chlorine bond, it will break homolytically due to UV ray. 1 electron will go to this chlorine, the other one will go to this chlorine. So we'll have 2 chlorine free radicals. Now this free radical will substitute the hydrogen, and for this reason this reaction is called a free radical substitution, since we are causing a substitution reaction using a free radical. We are substituting hydrogen with a free radical of chlorine. And this is what we have discussed right now. Alkanes also undergo exactly same reaction with bromine as well. So instead of it being chloromethane, it will be bromomethane. We'll have a bromine over here. We have Br2 over here. So exactly the same, just instead of chlorine, we'll have bromine. Even this step over here will be the same. Instead of a chlorine, there will be a bromine. Nothing different. Now we'll look into the mechanism of this reaction. This reaction over here occurs in 3 steps. The first step is called the initiation. This is the breaking of the Cl-Cl bond. So this is the initiation step where we get 2 chlorine free radicals, and we'll have UV light over here. Now the next step is the propagation step. Here a chlorine free radical will react with methane. So this is methane, and it will form chloromethane. So it will take away, at first it will take away one of the hydrogen. So it will take away one of the hydrogen and form HCl, and will be left with a CH3 free radical, a free radical of CH3. Now this free radical of CH3 will react with Cl2 And from here we'll get CH3Cl. This Cl will react with this free radical of CH3, and we'll have a Cl free radical remaining. And the final part of this mechanism is the termination reaction. It's when the free radicals involved in this propagation step react with each other or with themselves. So the chlorine free radical can react with the CH3 free radical. This will give us CH3Cl as well. We can have two chlorine free radicals reacting between themselves and forming Cl2. And we can also have two CH3 free radicals reacting between themselves, and from here we'll have C2H6. The mechanism is also the same for bromine. One thing you'll need to be careful about is this arrow must end on the chlorine. If I give the arrow like this, so this is wrong. So we need to be careful about where the arrow ends and where it starts. We'll also have to be very careful about making sure that this arrow is a half arrow. A full arrow will mean the movement of two electrons. We want to show the movement of one electron. Only one electron is going to the chlorine on the left. We can see here, for instance. So this one electron is moving to the red chlorine, the other one is moving to the blue chlorine. So we are having the movement of one electron, not two. That's it for this video.